So in the last video I talked a lot about arrays, which if you remember it was basically a collection of items. It was a primitive thing and it only had so yeah, we talked about three pros slash cons of it. The first one was that it had automatic memory allocation, so all of the memory is allocated right when it's initialized. The second one was that it was at a constant size, so you can't increase or decrease the capacity. And the third was that it has random access. So without having to cycle through any elements or have to, search for something, you can just right off the bat pull it out if you know what index you're looking for. So I mentioned that there's a way to circumvent the whole constant size thing, and that's what's called an array list. So this is the first of our abstract data types. This is a class that as instance variables, so backing data structures, you'll have. So this is the first time that we're actually creating a new class. The array, it was built in. We just do the two brackets and it works. But ArrayList, it's actually a new class. So we'll have something public class ArrayList or my ArrayList or something like that. And then for instance variables, so we know we want to use the same array thing because the whole issue of this was that we were trying to create a data structure that was essentially an array but didn't have the size restriction. So I'll do something like E R. So the way this works, E I'm saying is just some generic class, some generic object type, which if you look up Java generics, you'll find more information about it. I won't really talk about generics here because I'm mainly focusing on the data structures, but it's essential to kind of at least a little bit understand it for CSE 12 or any data structures class you might take. But in general, all I'm saying is, like in the last example when I did something like integer and two brackets to make an array, same thing, except I'm saying instead of specifying type integer, I'm saying type E. So this is some array of type E. So I'm gonna I'll initialize it to have a I want a space. To have a default value, a default capacity of 5. Right, so hopefully this makes relatively good sense. So in general, array lists, yeah, they'll have a default capacity of 5 in their backing array. So that's that. And then if you remember in the first video I made, I mentioned certain methods that all things should have, all data structures. Those were add, remove, contained, and size, where size returns, I'll go over all these. So add, basically I want to add some element to my data structure, so to my array list. Remove, I want to remove some element from my data structure. Contains, I want to see, does this thing that I'm specifying as a parameter exist? And size, I want to see how many elements I've added to my data structure. So right off the bat, we can think of some other things we might need. One thing that we would need would be an instance variable int, I'll call it size, equals 0. So this int data structure, it's basically just going to be a counter that keeps track of if I successfully add something to my data structure, I'll increment it. If I successfully remove something from my data structure, I'll decrement it. So it seems logical that if we want this size method to work, we would need some instance variable size. So for our purposes, those are really all you need. So now to get cracking down to how the methods would work, how we would actually implement these. So we know that we have two instance variables then. One of them is called R, and then it'll start with, I'll do this more correctly. So basically I start with a pointer, because remember in object-oriented design, especially with Java, we use pointers. So R is just a pointer, and it's pointing to some array of type E that has 5 slots. So R is pointing here. I hope that makes sense. That should be pretty intuitive from, it should make sense from your introductory Java class. And then I have some int called size, and this is a primitive, so it's not a pointer, it's the actual value. Or I guess it points to some, but I'll just have it as the actual value, whatever. But so there we go. So I have some size and some R. These are my two instance variables. So now let's say, so I'll dive down into each of these implementations. So add, in general, by practice, usually people put 2 add methods. Usually it'll be one that takes some object of type E, whatever E is that I specify when I create my data structure. It'll take that in, and then it'll add it to the end of the list. Or I'll have one where let's see. Yeah, so the first type just adds to the very end. So let's say I'm empty, it'll add here to the first slot. Let's say I have one element here, it'll add to the second slot, and so on. It just adds it to the end. The second one adds it to a specific index. So if I do add at index 0, that means if there's something here, I have to move everything down one and then insert into this new free slot. So right off the bat, we can see some problems. Let's say I add 3 things. So I do add 1, add 2, add 3. My array would look like this, right? Now let's say I do this one, and I add at index 0, I want to add a 4. So what do I have to do? Index 0 is filled currently. Oh, and then by the way, each time I did that, it would have incremented this to 4, right? To 3. Each time I added, it should have incremented it by 1. So the first add would make size 1, second add would do size equals 2, third add would do size equals 3. Now let's say I want to add to index 0. What do I have to do? I have to actually move each of these down 1 slot, and then I can add my new element. So right off the bat, you could see when we're dealing with a really big data structure, this would get pretty inefficient to have to move everything over 1 slot, 1 by 1, and then be able to add into our new slot. As you can tell, yeah, that'll take forever, because for n elements we have to do n moves pretty much. So yeah, as we can tell, an array list is very efficient for adding to the very end of it, but it's extremely inefficient for adding at the beginning, because we have to make room, do n operations to move each of these one thing over. So that's that. Now I'm going to talk about the remove method. So with remove methods in general, we'll have one that takes as a parameter an object of type E, and a second one that takes in an index. Oops. Index. So the first one will remove, so it'll search through the entire list, and then it'll see, does this object exist, and can I remove it? If so, remove it, and it would return true. If not, it wouldn't affect the data structure, and it would return false. This one, on the other hand, it sees, did the person pass in a valid index? If so, I'll remove whatever element is at that index. If not, throw an error maybe, something like that. But yeah, so that's how these two differ. Essentially, this remove method is the same thing as this contains method, except contains just searches through, and if the object exists, it doesn't affect the object at all. It just returns true, or if the object doesn't exist, it returns false. Remove method, it cycles through. If the object is found and I can successfully remove it, it does it and returns true. If it's not found, or for whatever reason I can't remove it, it returns false. So that is how this specific remove method and this contains method kind of go hand in hand. So same thing applies for removing. If I were to just remove at the very end, I just pretty much scribble it out, right? And I decrement size. But if I'm trying to remove from the beginning, that means I would have to scribble this out, move this here, move this here, and move that there. So removing from the beginning also, as you can see, takes n operations, because I start from the end and I keep on shifting each thing one thing further, or start from the beginning, whatever. But you have to shift every element back one index. So very inefficient. So, oh, and then going back to the size method you would just return this size as long as you were keeping track of it correctly. So now a basic summary of array lists, what you should know is basically just like I did with the array video, their main features, their pros and cons. So one large feature is that you can have easy random access. If I'm trying to get an element from any specific position, I can just call, oh, actually I haven't mentioned, you probably have a get method too, or something like that, where you pass in a parameter, an index, and you get whatever element is at that index. But yeah, random access, it would take constant time to find an element at any given space, since we know exactly where in memory each element is. Because remember, in the last video I explained arrays, it's contiguous in memory. The second thing is that it's very slow to add, or I'll say modify. Modify beginning. When you go into time complexities later on, it's actually big O of n. But basically what that means is it takes n operations to add or remove from the beginning. The third thing is it's very fast to modify the end. So you'll learn constant time. These are all time complexities that you'll learn later on in the class, but essentially what it means is it takes one operation. You just do your thing at the end and it does it. You don't have to cycle or do multiple operations depending on your sample size. No matter how many elements you have, it could be 5 billion. If you want to add something to the end or remove it from the end, it takes just as long as if you only had one element. So that's basically that. And now 4. The last video, well, I actually won't write this as an actual array list feature, because now this is going to be a feature for any list that we make, which you'll learn about more in the next videos. But now, I mentioned making an array list lets us have unlimited size, so unlimited capacity. We can keep on adding and adding and adding, and to the user it should look limitless. So how do we do that? With an array list, it's very easy. I mentioned we have some pointer to our backing array that by default starts at 5 elements. Now let's say I do the add method 5 times, and now my backing array is full. So what do? In my add method, I could easily put some if statement that says if. So I'll just say it in terms of pseudocode, I'll just say it, but if you're actually programming it, it would basically be written exactly as how it sounds. But I want to check if my size equals my capacity. So if I have just as many elements as how many I can fit, then I would create a new array, and by default people usually do twice the initial size. You can do whatever you want, but the most efficient is usually doing twice the previous one size. So I make a new one. I copy all the original elements into their corresponding from start to end indices in this one. And then I point my pointer to that new array. So now my backing array is this one. Garbage collector will come through and destroy this one, and then I'll be good. So yeah, that is basically how we can avoid that issue with this data structure and many more. It's a very basic primitive if statement that checks if my size equals capacity. Let me create a new one, copy all my elements, and now point my backing data structure to that new one. Yeah. So in the next video, I believe I will be talking about linked lists. But yeah, we'll get to that later. But that's essentially the sum of array lists. Easy to get to something at the beginning. I mean, slow for the beginning, fast at the end, and these are just characteristics of arrays. And random access, which is also a characteristic of an array.